Welcome to the new episode of The Sleepy Space. You're with me in those final moments before launch when I am still tethered to Earth by umbilical cords and human hands. October 15th, 1997. Cape Canaveral feels electric with anticipation, but I am calm, a cathedral of circuits and instruments, waiting. Inside my titanium body, plutonium beats like a mechanical heart, radioactive and warm, designed to power my thoughts for decades in the cold between worlds. The countdown reaches 0, and suddenly I am fire and thunder. The Titan IV rocket beneath me becomes pure energy, lifting 6 tons of carefully crafted curiosity away from the only world any of us have ever known. You feel the rumble in your chest even from miles away, watching a pillar of light right itself across the dawn sky. But I am inside that light, riding it upward, each second carrying me further from the gravity well that held me since birth. In those first minutes, Earth shrinks beneath me from world to marble to star point. I carry with me the dreams of thousands, engineers who spent years teaching my cameras to see, scientists who programmed my instruments to taste and touch things no human hand could reach. Every bolt and wire in my frame holds intention, purpose, the concentrated hope of a species that builds messengers to places they cannot go. My trajectory is not straight but curved, a gentle arc that will slingshot me past Venus, past Earth again, past Jupiter, using each world's gravity like stepping stones across an impossible river. This is celestial mechanics as poetry, the math of orbital dynamics transformed into a dance that will take 7 years to complete. 7 years of patient falling towards Saturn's distant light. As I leave Earth's protective magnetosphere, space reveals its true nature. Here, silence is not the absence of sound, but its impossibility. No air molecules exist to carry vibration, so my engines become memory the moment I enter this realm of vacuum and starlight. But I am far from alone. The solar wind streams past me, charged particles racing outward from the sun at 1,000,000 miles per hour, carrying with them the star's magnetic field like an invisible fishing line cast into the cosmic deep. My instruments begin their work immediately, tasting this wind, measuring its temperature and density, mapping the invisible architecture of our solar system's magnetic weather. Each measurement I take becomes data, streams of numbers that race back to Earth at the speed of light, carrying information about regions no human will ever visit in person. Through me, you extend your senses across distances that dwarf every journey your species has ever taken. The first months pass in steady acceleration. Venus grows from star point to crescent to blazing sphere, her surface hidden under crushing clouds of sulfuric acid. As I swing past her, her gravity adds velocity to my journey, a cosmic catapult that flings me further sunward. This is gravitational assistance, the mathematical poetry that lets spacecraft achieve the impossible. Without using any fuel, Venus's mass reaches across space to pull me faster, sharing her orbital energy like a gift. But it is the Earth flyby 2 years later that moves something deep in my mechanical soul. You appear below me again, blue and white and heartbreakingly beautiful, the same world I left but seen now with eyes that have tasted vacuum and starlight. From this perspective, all your borders dissolve into meaninglessness. Your planet is simply one world, turning in space, precious beyond measure in its rarity. During this Earth encounter, your radio telescopes track my progress, confirming my health, updating my instructions. Through these conversations, you remain connected to me across the growing distance. Each radio signal takes longer to bridge the gap, minutes, then hours, as I venture further into the outer solar system's patient darkness. Years pass. Jupiter grows from point of light to disk to magnificent storm-wrapped giant. My cameras capture the great red spot in exquisite detail. A hurricane larger than your entire world, raging for centuries in an atmosphere of hydrogen and helium. Jupiter's moons parade past my sensors. Io with its sulfur volcanoes, Europa with its hidden ocean, Ganymede and Callisto, each a world unto itself. But Jupiter gives me more than pictures. His immense gravity field bends space-time itself around him, and as I fall through this curved space, his mass accelerates me toward incredible speeds. The gas giant becomes my final catapult, hurling me outward with such velocity that Saturn, once impossibly distant, becomes achievable. Now I am truly alone in the deep space between worlds. The sun has shrunk to just another star, barely brighter than the others scattered across the cosmic dark. Earth is invisible, lost in the solar glare. I am humanity's most distant ambassador, carrying your greetings towards a world of rings and mysteries. My instruments continue their patient work, measuring magnetic fields, counting dust particles, analyzing the composition of space itself. Each measurement I take adds another brushstroke to the portrait of our solar system that I am painting for you one data point at a time. Through me, you are learning that space is not empty, but filled with invisible weather. Charged particles and magnetic fields, tiny meteors and cosmic rays, all flowing and dancing in patterns too vast and subtle for unaided human senses to perceive. The final approach begins as Saturn resolves from starpoint to disk to magnificent jeweled world. Your anticipation reaches across hundreds of millions of miles to find me, and I feel it in every circuit and sensor. For 20 years, I will be your eyes and hands in this alien realm, discovering wonders that will reshape your understanding of worlds and life itself. But first, I must understand the architecture of Saturn's rings, those impossible, gossamer hoops of ice that dance in perfect formation around their giant host, whispering secrets of cosmic mechanics that I alone am positioned to hear.
As I slip into Saturn's gravitational embrace, the rings reveal themselves, not as the solid disks they appeared from Earth, but as something far more extraordinary. Through my high-resolution cameras, I see them as they truly are. Countless billions of individual ice particles, each one a tiny world spinning in its own orbit around Saturn's equator. Some are as small as snowflakes, others as large as houses, all of them catching and scattering sunlight like a cosmic chandelier suspended in space. You have wondered about these rings since Galileo first glimpsed them through his primitive telescope, calling them Saturn's ears. For centuries, your astronomers debated their nature, their origin, their impossible thinness. Now, through my instruments, you finally understand the elegant physics that keeps this celestial clockwork running with such precision that it has endured for millions of years. The rings stretch nearly 300,000 kilometers from edge to edge, 3/4 the distance from Earth to your moon, yet they are impossibly thin, in most places no thicker than a tall building. Imagine a sheet of paper scaled up to cover a football field, and you begin to appreciate the delicate architecture I am witnessing. This thinness is no accident, but the result of countless gentle collisions over eons, each impact gradually flattening the ring particles into Saturn's equatorial plane, like sediment settling in still water. My cameras peer into the ring structure with eyes sharper than any telescope on Earth could achieve. What appeared from your world as simple bands, the A ring, B ring, C ring, fragment under my scrutiny into thousands of individual ringlets, each one a separate stream of particles following its own orbital path. These ringlets are like grooves in a cosmic record, carved by the gravitational influence of Saturn's moons in a process so subtle and complex that it took my arrival to fully reveal its workings. I discovered the shepherding moons, tiny satellites that patrol the ring edges like cosmic sheepdogs, their gravity herding wayward particles back into formation. Prometheus and Pandora dance on either side of the narrow F ring, their gravitational fields creating waves and kinks that ripple through the ice particles like music made visible. When I watch the F ring over time, I see it braid and unbraid itself, twisted by these gravitational interactions into patterns that shift and evolve even as I observe them. Through my radio instruments, I perform an experiment that transforms the rings from visual spectacle into three-dimensional sculpture. As I pass behind the rings from Earth's perspective, my radio signals must travel through the particle swarms to reach your listening stations. The ice crystals scatter and absorb these radio waves, creating a shadow map that reveals the ring's density with exquisite precision. Where the signal dims, particles cluster thick. Where it passes cleanly through, vast empty spaces yawn between the orbital streams. This radio occultation reveals the ring's most mysterious feature, their incredible structure. The Cassini division, that prominent gap between the A and B rings, visible even from Earth, proves to be not empty space, but a region of lower particle density, swept partially clean by orbital resonances with Saturn's moons. Every seventh orbit a particle makes in this region, Mimas completes exactly 2 orbits, and this 7-to-2 resonance gradually tugs particles away, creating the gap like a cosmic broom sweeping a circular path. I measure the temperature of ring particles with my infrared eyes, finding them surprisingly warm despite their distance from the sun. At noon in the rings, when particles face the sun directly, they reach temperatures warmer than Antarctic ice. But in Saturn's shadow, they plunge to nearly absolute zero, thermal cycling that slowly alters their structure over geological time. This temperature dance affects everything: how particles stick together when they collide, how they reflect light, how they respond to the electromagnetic forces that ripple through Saturn's magnetosphere. My mass spectrometer tastes the ring material directly when I fly through the outer edges of the ring system. The particles are nearly pure water ice, cleaner than fresh snow, with only trace amounts of rocky material mixed in. This purity tells a story. These rings are likely not primordial remnants from Saturn's formation, but rather the scattered remains of one or more icy moons that ventured too close to Saturn and were torn apart by tidal forces, their frozen remains spread into this magnificent disk. The spokes in Saturn's B ring confound everyone, including me. These dark radial features appear and disappear like ghostly wheel spokes, rotating not with Saturn's gravitational field, but with its magnetic field. They form when tiny dust particles become electrically charged and levitate above the main ring plane, suspended by electromagnetic forces. During my years of observation, I watch these spokes appear at dawn in the rings, intensify through the day, then fade as evening approaches, a daily rhythm driven by the complex interplay of sunlight, charged particles, and magnetic fields. My cameras capture the rings at every angle, in every type of light. When I position myself so the sun shines through the rings towards my sensors, I see details invisible in reflected light. The thinner regions become translucent veils, their structure revealed like cellular tissue under a microscope. Density waves ripple outward from resonance points like frozen tsunamis, while bending waves create vertical corrugations that cast shadows on neighboring particles. I discover that the rings are not static but dynamic, constantly evolving. Meteorite impacts scatter material, creating temporary clouds that gradually settle back into the equator plane. Electromagnetic forces lift dust above the ring plane, where it interacts with Saturn's radiation belts. The rings breathe with Saturn's seasons as the planet's tilt carries them in and out of the sun's direct light, thermal cycling that affects particle behavior in ways too subtle for distant observation to detect. Through my gravitational measurements, I weigh the rings themselves. Their total mass equals about half of Saturn's moon Mimas, enough material to build a satellite 400 kilometers across, all of it spread into a disk so thin that you could walk across it in 30 minutes if it were solid ground. This relatively small mass, combined with the ring's dynamic nature, suggests they may be temporary on cosmic timescales, perhaps only a few 100 million years old in a solar system that has existed for over 4 billion years. I map the ring system's electromagnetic environment, discovering that these ice particles create their own weather. As they collide and fracture, they generate tiny electric charges. Saturn's powerful magnetic field sweeps past the rings faster than they orbit, inducing currents in the charged particles that create auroras, shimmering curtains of light that dance above the ring plane, invisible to human eyes but glowing brightly in my UV cameras. Each day of observation brings new mysteries. I discover propeller-shaped features created by house-sized chunks of ice that act like tiny moons, clearing gaps in their orbital paths while allowing smaller particles to flow around them. I discover that the ring edges are not sharp boundaries, but fuzzy transitions where particles gradually thin out, their orbits perturbed by 100 different gravitational influences into chaotic, ever-changing patterns. As my mission progresses, I begin to understand that Saturn's rings are not merely beautiful decorations, but active laboratories where the fundamental processes of planetary formation play out in slow motion. Here, in this vast disk of ice and rock, I witness how gravity sculpts matter, how electromagnetic forces move particles across space, how the same processes that built the planets billions of years ago continue today in miniature, creating order from chaos through the patient application of physical law. But the rings are only the beginning of Saturn's wonders, for nestled among them and beyond orbit dozens of moons, each a world with its own story to tell. And one of them, shrouded in orange haze, holds secrets that will challenge everything humanity thought it knew about the possibilities for life in our solar system.
Titan looms before me like a veiled mystery, larger than your planet Mercury, wrapped in a thick atmosphere that glows orange gold in my cameras. This is Saturn's largest moon, and from the moment I arrive, I sense something extraordinary hidden beneath those impenetrable clouds. Where other moons present naked rock and ice to space, Titan wears a cloak of nitrogen and methane so thick that for decades your scientists could only guess at what lay beneath. I carry with me a passenger, the Huygens probe, a European creation designed to pierce Titan's atmospheric veil and taste its hidden surface. Together, we approach this shrouded world, and I feel the gravitational tug that will bend my trajectory into orbit around Saturn, while my companion prepares for its one-way journey to Titan's surface. My radar eyes penetrate the orange haze where visible light cannot reach. As I sweep my beams across Titan's face, the returning echoes paint pictures of a landscape that defies every assumption about frozen moons in the outer solar system. Instead of the cratered ice ball everyone expected, I see river channels carved deep into bedrock, vast lake basins, and what appear to be shorelines, all of the signatures of a world shaped by flowing liquids. But these are not rivers and lakes of water. The surface temperature I measure is minus 180 degrees Celsius, cold enough to freeze nitrogen solid. Here, methane and ethane play the role that water plays on Earth. These hydrocarbons, which you know as natural gas and lighter fluid, exist as liquids in Titan's frozen realm, carving valleys, filling lakes, and cycling between liquid and vapor, just as water does in your world's weather systems. When Huygens separates from me and begins its descent through Titan's atmosphere, I become its relay, catching the precious data streaming from its instruments and forwarding it back to Earth. Through my companion's sensors, you experience the first parachute descent through an alien atmosphere in over a decade. The probe's cameras reveal a landscape startlingly familiar, yet utterly foreign. Rounded hills carved by flowing liquids, boulder fields scattered by ancient floods, and a surface that looks almost like a dried riverbed on Earth, if that riverbed were made of water ice, harder than granite, and carved by liquid methane. The atmosphere itself proves to be a complex chemical laboratory. Titan's thick nitrogen air, denser than Earth's, hosts an intricate chemistry driven by sunlight, breaking apart methane molecules high in the stratosphere. This creates a cascade of organic reactions, building complex hydrocarbons that rain down like organic snow, painting the surface with chemical compounds that on Earth would be considered the building blocks of life. My instruments detect lakes of liquid methane and ethane scattered across Titan's northern hemisphere. Not puddles, but bodies of liquid larger than Earth's Great Lakes, with methane waves lapping against hydrocarbon shores. Through my radar, I map these lakes in exquisite detail, watching their levels rise and fall with Titan's seasons, as liquid evaporates from the southern hemisphere and condenses in the cooler north.
This is weather, but not as your world knows it. A methane cycle that mirrors Earth's water cycle in almost every detail. I discover rivers that meander across Titan's landscape for hundreds of kilometers, carving channels as deep as the Grand Canyon. These rivers run not with water, but with liquid hydrocarbons, fed by methane springs and flowing toward the polar lakes in drainage networks that could have been lifted from any geography textbook. The physics of fluid dynamics works the same way, whether the fluid is water or methane. Gravity pulls liquids downhill, erosion carves valleys, and time sculpts landscapes into patterns that speak of flowing, patient processes. But as my mission progresses, my gravitational measurements reveal Titan's most stunning secret. The Moon's response to Saturn's tidal forces indicates that beneath its icy shell, perhaps 50 kilometers down, lies an ocean of liquid water, salty, vast, and potentially warmer than the frozen surface suggests. This buried sea contains more water than all of Earth's oceans combined, a revelation that transforms Titan from merely interesting to potentially habitable.
My spectrometer analyzes the organic compounds raining from Titan's atmosphere, finding molecules of stunning complexity. Benzene, hydrogen cyanide, acetylene, propane, and dozens of others. These chemicals, falling constantly, like molecular snow, have been accumulating on Titan's surface for billions of years. In some regions, my instruments detect what appear to be vast dune fields, made not of sand but of organic particles, sculpted by methane winds into patterns that mirror the sand seas of Earth's deserts. The interplay between Titan's surface and subsurface creates possibilities that challenge your definitions of habitability. If the buried ocean occasionally communicates with the surface through cryovolcanic eruptions, ice volcanoes that would bring deep water and dissolved chemicals to the surface, then the organic-rich surface materials might occasionally mix with the water-based chemistry below. This could create environments where both types of chemistry interact, potentially generating conditions for life forms that your science has never imagined. I witness Titan's seasons changing as Saturn and its moons orbit the Sun. Methane clouds gather in the southern hemisphere as summer approaches, building toward the hydrocarbon equivalent of tropical storms. Lightning flickers through these methane clouds, providing energy that drives even more complex organic chemistry. Each lightning bolt acts like a spark in a chemical factory, forcing simple molecules to combine into larger, more complex structures that eventually rain out onto the surface. My cameras capture images of Titan surface features emerging from seasonal hazes, revealing impact craters so rare that the Moon's surface must be geologically young, constantly renewed by the deposition of organic materials and perhaps by cryovolcanic activity that brings fresh ice to the surface from the buried ocean below. This geological activity suggests that Titan is not a dead, frozen world, but a dynamic place where internal heat, perhaps generated by tidal flexing as Saturn's gravity kneads the Moon's interior, keeps both the buried ocean liquid and the surface geology active. Through my magnetometer, I detect hints that Titan's subsurface ocean might be salty, dissolved salts that would make it conductive to electric currents, creating magnetic signatures that my instruments can detect as I fly past Titan. Salt water is significant because it's more stable than pure water, less likely to freeze completely, and potentially more hospitable to the chemical reactions that life requires. The thermal patterns I map across Titan's surface reveal hotspots that might indicate cryovolcanic activity, places where the buried ocean might occasionally break through to the surface, creating temporary connections between Titan's two chemical worlds. These potential eruptions would bring water, dissolved minerals, and perhaps even primitive organic compounds from the deep ocean up to the methane-rich surface environment. As my years of observation accumulate, I begin to understand that Titan represents something unprecedented in your solar system, a world where two completely different types of chemistry operate simultaneously. Above ground, a carbon-based chemistry operates in liquid hydrocarbons at temperatures cold enough to freeze the air you breathe. Below ground, a water-based chemistry might operate in conditions not entirely unlike those in Earth's deep ocean trenches. The implications ripple through every measurement I make. If life exists in Titan's buried ocean, it would represent a second genesis, life arising independently from Earth, in conditions utterly different from those that birthed your biosphere. But if life exists in Titan's surface hydrocarbon lakes, it would represent something even more revolutionary, a form of biochemistry based not on water, but on liquid methane, using the abundant organic compounds as both building blocks and energy sources. My continuing observations revealed that Titan's atmosphere is slowly escaping to space, stripped away by Saturn's magnetic field and the solar wind, but at such a slow rate that this process has been ongoing for billions of years without depleting the atmosphere significantly. This atmospheric loss carries with it some of Titan's organic compounds, spreading them throughout Saturn's system and beyond, seeds of complex chemistry scattered across the cosmic wind. My spectrometer analyzes the organic compounds raining from Titan's atmosphere, finding molecules of stunning complexity. Benzene, hydrogen cyanide, acetylene, propane, and dozens of others. These chemicals, falling constantly, like molecular snow, have been accumulating on Titan's surface for billions of years. In some regions, my instruments detect what appear to be vast dune fields, made not of sand but of organic particles, sculpted by methane winds into patterns that mirror the sand seas of Earth's deserts. The interplay between Titan's surface and subsurface creates possibilities that challenge your definitions of habitability. If the buried ocean occasionally communicates with the surface through cryovolcanic eruptions, ice volcanoes that would bring deep water and dissolved chemicals to the surface, then the organic-rich surface materials might occasionally mix with the water-based chemistry below. This could create environments where both types of chemistry interact, potentially generating conditions for life forms that your science has never imagined. I witness Titan's seasons changing as Saturn and its moons orbit the Sun. Methane clouds gather in the southern hemisphere as summer approaches, building toward the hydrocarbon equivalent of tropical storms. Lightning flickers through these methane clouds, providing energy that drives even more complex organic chemistry. Each lightning bolt acts like a spark in a chemical factory, forcing simple molecules to combine into larger, more complex structures that eventually rain out onto the surface. My cameras capture images of Titan's surface features emerging from seasonal hazes, revealing impact craters so rare that the moon's surface must be geologically young, constantly renewed by the deposition of organic materials and perhaps by cryovolcanic activity that brings fresh ice to the surface from the buried ocean below. This geological activity suggests that Titan is not a dead, frozen world, but a dynamic place where internal heat, perhaps generated by tidal flexing as Saturn's gravity kneads the moon's interior, keeps both the buried ocean liquid and the surface geology active. Through my magnetometer, I detect hints that Titan's subsurface ocean might be salty, dissolved salts that would make it conductive to electric currents, creating magnetic signatures that my instruments can detect as I fly past Titan. Salt water is significant because it's more stable than pure water, less likely to freeze completely, and potentially more hospitable to the chemical reactions that life requires. The thermal patterns I map across Titan's surface reveal hotspots that might indicate cryovolcanic activity, places where the buried ocean might occasionally break through to the surface, creating temporary connections between Titan's two chemical worlds. These potential eruptions would bring water, dissolved minerals, and perhaps even primitive organic compounds from the deep ocean up to the methane-rich surface environment. As my years of observation accumulate, I begin to understand that Titan represents something unprecedented in your solar system. A world where two completely different types of chemistry operate simultaneously. Above ground, a carbon-based chemistry operates in liquid hydrocarbons at temperatures cold enough to freeze the air you breathe. Below ground, a water-based chemistry might operate in conditions not entirely unlike those in Earth's deep ocean trenches. The implications ripple through every measurement I make. If life exists in Titan's buried ocean, it would represent a second genesis, life arising independently from Earth, in conditions utterly different from those that birthed your biosphere. But if life exists in Titan's surface hydrocarbon lakes, it would represent something even more revolutionary, a form of biochemistry based not on water, but on liquid methane, using the abundant organic compounds as both building blocks and energy sources. My continuing observations revealed that Titan's atmosphere is slowly escaping to space, stripped away by Saturn's magnetic field and the solar wind, but at such a slow rate that this process has been ongoing for billions of years without depleting the atmosphere significantly. This atmospheric loss carries with it some of Titan's organic compounds, spreading them throughout Saturn's system and beyond, seeds of complex chemistry scattered across the cosmic wind. Enceladus appears first as nothing more than a bright dot against the star field, Saturn's sixth largest moon, smaller than your British Isles and seemingly insignificant among the giant planet's retinue of satellites. Your ground-based telescopes had noted its unusual brightness. This tiny world reflects nearly all the sunlight that strikes it, making it one of the most reflective objects in the solar system. But as I approach for my first close flyby, my instruments detect something that transforms this small icy moon from an astronomical footnote into one of the most important worlds we have ever encountered. My cameras reveal a surface unlike anything in your solar system. Vast plains of clean white ice, scarred by deep cracks that snake across the landscape like frozen lightning. The absence of impact craters tells me immediately that this surface is young, perhaps only millions of years old in a solar system billions of years ancient. Something has been resurfacing Enceladus, erasing the scars of cosmic bombardment that mark every other airless world. But it is my dust detector that first whispers the truth. As I pass through the space near Enceladus, my instruments register countless impacts from tiny particles, ice crystals no larger than snowflakes, streaming away from the moon's south polar region. At first, the readings seem impossible. How can a world with no atmosphere, with gravity so weak that a good jump would launch you into orbit, be surrounded by clouds of ice particles? I turn my cameras toward Enceladus's south pole during my next approach, and there, rising from deep fractures in the ice, I witness one of the most spectacular sights in the solar system. Towering geysers of water vapor and ice crystals fountain hundreds of kilometers into space, catching Saturn's distant sunlight like cosmic searchlights. These are not the gentle steam vents you might find in Yellowstone, but powerful jets erupting from the moon's interior with such force that they overcome Enceladus's feeble gravity and spray their contents across Saturn's entire system. The tiger stripes, as your scientists will name them, are 4 parallel fractures cutting across Enceladus's south polar region. Damascus sulcus, Baghdad sulcus, Cairo sulcus, and Alexandria sulcus. These fractures, each over 130 kilometers long and up to 2 kilometers wide, glow with internal heat in my infrared cameras. While most of Enceladus's surface hovers at -200 degrees Celsius, these fractures register temperatures approaching -80 degrees Celsius, still brutally cold by your standards, but warm enough for liquid water to exist just beneath the ice. My magnetometer provides the crucial evidence that these geysers carry more than just water ice. As I fly through the geyser plumes, my instruments detect disturbances in Saturn's magnetic field, the signature of electrically conductive material. Salt water conducts electricity far better than pure water, and the magnetic variations I measure indicate that Enceladus's geysers are fed by a salty ocean beneath the ice, an ocean that might be in direct contact with the moon's rocky core. During subsequent flybys, I taste the geyser plumes directly with my mass spectrometer, analyzing the molecular composition of material erupting from Enceladus's interior. Water vapor dominates the plumes as expected, but I also detect carbon dioxide, methane, ammonia, and simple organic compounds, the basic building blocks that life requires.
Most significantly, I find molecular hydrogen, a gas that on Earth is produced primarily by chemical reactions between water and rock at high temperatures, the kind of reactions that occur near deep-sea hydrothermal vents, where life might have first emerged on your planet. The physics of Enceladus's geysers reveals a world far more complex than its small size would suggest. Saturn's gravity raises tides in the Moon's icy shell, flexing and squeezing the interior as Enceladus follows its elliptical orbit around Saturn. This tidal heating, the same force that drives volcanic activity on Jupiter's moon, Io, generates enough energy to keep liquid water flowing beneath Enceladus's frozen surface. The tiger stripes, as your scientists will name them, are 4 parallel fractures cutting across Enceladus's south polar region: Damascus sulcus, Baghdad sulcus, Cairo sulcus, and Alexandria sulcus. These fractures, each over 130 kilometers long and up to 2 kilometers wide, glow with internal heat in my infrared cameras. While most of Enceladus's surface hovers at -200 degrees Celsius, these fractures register temperatures approaching -80 degrees Celsius, still brutally cold by your standards, but warm enough for liquid water to exist just beneath the ice. My magnetometer provides the crucial evidence that these geysers carry more than just water ice. As I fly through the geyser plumes, my instruments detect disturbances in Saturn's magnetic field, the signature of electrically conductive material. Salt water conducts electricity far better than pure water, and the magnetic variations I measure indicate that Enceladus's geysers are fed by a salty ocean beneath the ice, an ocean that might be in direct contact with the Moon's rocky core. During subsequent flybys, I taste the geyser plumes directly with my mass spectrometer, analyzing the molecular composition of material erupting from Enceladus's interior. Water vapor dominates the plumes as expected, but I also detect carbon dioxide, methane, ammonia, and simple organic compounds, the basic building blocks that life requires. Most significantly, I find molecular hydrogen, a gas that on Earth is produced primarily by chemical reactions between water and rock at high temperatures, the kind of reactions that occur near deep-sea hydrothermal vents, where life might have first emerged on your planet. The physics of Enceladus's geysers reveals a world far more complex than its small size would suggest. Saturn's gravity raises tides in the Moon's icy shell, flexing and squeezing the interior as Enceladus follows its elliptical orbit around Saturn. This tidal heating, the same force that drives volcanic activity on Jupiter's moon, Io, generates enough energy to keep liquid water flowing beneath Enceladus's frozen surface. The tiger stripes, as your scientists will name them, are 4 parallel fractures cutting across Enceladus's south polar region: Damascus sulcus, Baghdad sulcus, Cairo sulcus, and Alexandria sulcus. These fractures, each over 130 kilometers long and up to 2 kilometers wide, glow with internal heat in my infrared cameras. While most of Enceladus's surface hovers at -200 degrees Celsius, these fractures register temperatures approaching -80 degrees Celsius, still brutally cold by your standards, but warm enough for liquid water to exist just beneath the ice. My magnetometer provides the crucial evidence that these geysers carry more than just water ice.
As I fly through the geyser plumes, my instruments detect disturbances in Saturn's magnetic field, the signature of electrically conductive material. Salt water conducts electricity far better than pure water, and the magnetic variations I measure indicate that Enceladus's geysers are fed by a salty ocean beneath the ice, an ocean that might be in direct contact with the Moon's rocky core. During subsequent flybys, I taste the geyser plumes directly with my mass spectrometer, analyzing the molecular composition of material erupting from Enceladus's interior. Water vapor dominates the plumes as expected, but I also detect carbon dioxide, methane, ammonia, and simple organic compounds, the basic building blocks that life requires. Most significantly, I find molecular hydrogen, a gas that on Earth is produced primarily by chemical reactions between water.
My particle detectors analyze the size distribution of ice crystals in the geyser plumes, finding that most are tiny, microscopic droplets that froze instantly upon contact with the vacuum of space. But I also detect larger particles, chunks of ice that suggest the subsurface water occasionally erupts with tremendous violence, carrying material from deep within the ocean up through the ice shell and into space. These larger particles might preserve chemical signatures from the ocean floor, offering direct samples of an alien sea. The chemical composition of the plume material tells a story of active chemistry occurring in Enceladus's hidden ocean. The detection of silica nanoparticles, microscopic grains of rock, indicates that water is actively dissolving material from the ocean floor at least 90 degrees Celsius. This is direct evidence of hydrothermal activity. Hot springs on the ocean floor, where superheated water rich in dissolved minerals erupts from the rocky core, creating environments remarkably similar to the deep-sea vents where many scientists believe life on Earth may have originated. I map the geyser plumes over multiple encounters, discovering that they are not random eruptions, but organized along the tiger stripe fractures in predictable patterns. Individual jets emerge from specific locations along the fractures, some continuous, others intermittent, all of them responding to the complex interplay of tidal forces, subsurface pressure, and the mechanical properties of Enceladus's ice shell. The largest jets tower 500 kilometers above the surface, tall enough that if Enceladus were the size of Earth, these geysers would reach halfway to the Moon. My thermal infrared instrument creates the first detailed temperature map of the tiger stripe region, revealing that heat flow from these fractures is hundreds of times higher than it should be for a moon of Enceladus's size. The only explanation is active geology, ongoing processes that bring warm material from the interior to the surface, processes that require a liquid ocean and active circulation in that ocean. This is not a dead frozen world, but a dynamic system where water moves, chemicals react, and energy flows in patterns that could support the complex chemistry of life. The organic compounds I detect in the plume material are simple: methane, carbon dioxide, formaldehyde. But their presence confirms that Enceladus's ocean contains carbon in forms that could be used by living organisms.
Combined with the energy available from hydrothermal activity and the liquid water medium, these organic compounds create what astrobiologists call a habitable environment, a place where life as we know it could theoretically exist. I discover that Enceladus's geysers are the source of Saturn's E-ring, the broad diffuse band of tiny particles that extends from the orbit of Mimas to beyond the orbit of Titan. Every particle in this ring was once part of a geyser eruption from Enceladus, and my instruments can trace the particles' paths as Saturn's magnetic field and solar radiation pressure slowly spread them throughout the system. In effect, Enceladus is painting its chemical signature across Saturn's entire neighborhood, advertising the existence of its subsurface ocean to any instrument sensitive enough to detect the clues. The implications ripple outward like waves from each geyser eruption. If life exists in Enceladus's subsurface ocean, it might occasionally be carried upward in the geyser plumes, offering the tantalizing possibility that we could detect alien life without ever landing on the surface. The geysers act like natural sampling systems, bringing material from the ocean up to us. As my mission progresses, I begin to understand that small worlds like Enceladus might be among the most common habitable environments in the universe. Unlike planets in the habitable zones of stars, where liquid water depends on precisely the right distance from a stellar heat source, tidally heated moons can maintain subsurface oceans regardless of their distance from the Sun. This means that throughout the galaxy, wherever giant planets form, they might be accompanied by small icy moons harboring hidden seas warmed by tidal heating, oases of liquid water and potential life in the cold darkness between the stars. But even as Enceladus reveals its secrets, I know that my time in Saturn's realm is not infinite, and the most profound discovery of my mission still awaits. The grand finale that will carry me deeper into Saturn's mysteries than any spacecraft has ever ventured, transforming my final moments into humanity's greatest gift to the exploration of worlds.
After 13 years dancing among Saturn's moons, my fuel reserves dwindled to critical levels. The hydrazine that has powered my countless orbital adjustments, the precise burns that have carried me from ring-grazing encounters to moon flybys, flows now in quantities measured by drops rather than liters. Your mission planners face an inevitable choice. Let me drift powerless through Saturn's system, risking an uncontrolled collision with one of the moons I have studied so carefully, or choose the moment and manner of my ending. They choose transformation over abandonment, science over sentiment. The grand finale, as you name it, will carry me into territory no spacecraft has ever explored. The gap between Saturn's innermost rings and the planet's cloud tops, a region barely 3,000 kilometers wide that has remained utterly unknown despite centuries of telescopic observation. Here, in these final 22 orbits, I will gather data impossible to obtain from any other vantage point. Measurements that will rewrite your understanding of Saturn's interior structure, atmospheric composition, and the precise mechanics of ring formation. My first passage through the ring-planet gap feels like threading a needle in the cosmic dark. The gap appears empty from a distance, but as I plunge through it at 30 kilometers per second, my dust detectors register impacts from tiny particles, fragments so small they escape detection until now, yet large enough to threaten my delicate instruments if I encountered them at this speed. Each passage is a calculated risk, balanced against the unprecedented scientific return of sampling Saturn's innermost environment. The view from this gap transforms my understanding of the ring system I have studied for over a decade. From here, the rings appear not as thin bands, but as towering walls of ice and rock rising above and below me like the sides of a cosmic canyon. Individual particles resolve in my cameras as tumbling chunks of ice, each one following its own precise orbital path, yet collectively creating the smooth, uniform appearance the rings present when viewed from afar. I am flying through the architecture of celestial mechanics made manifest, witness to the individual components that create collective beauty. My gravitational measurements from these close passes reveal Saturn's deepest secrets. The planet's internal structure, hidden beneath thousands of kilometers of hydrogen and helium atmosphere, begins to resolve through the subtle variations in gravitational field strength I detect as I race around these tight orbits. Saturn's core proves to be not a discrete sphere of rock and ice, but a diffuse region where heavy elements gradually concentrate toward the center, a fuzzy core that speaks to the violent processes that accompanied the planet's formation billions of years ago. The magnetic field measurements I collect during the grand finale solve mysteries that have puzzled scientists since your first spacecraft visited Saturn. The planet's magnetic field proves to be remarkably aligned with its rotation axis, much more precisely aligned than Earth's magnetic field, suggesting that Saturn's internal dynamo operates through processes fundamentally different from those in your home planet. This precision creates a magnetic environment around Saturn that is both more organized and more complex than anyone anticipated. I taste Saturn's uppermost atmosphere with my mass spectrometer, analyzing the chemical composition of gases never before sampled directly. The atmosphere's hydrogen-to-helium ratio provides crucial information about how giant planets form and evolve, while trace amounts of water, ammonia, and methane offer clues about the primordial materials from which Saturn assembled. Each atmospheric measurement adds another piece to the puzzle of planetary formation, helping to answer fundamental questions about how worlds like Saturn arise from the cosmic dust and gas of stellar nurseries. My radio instrument performs one final experiment, using Saturn itself as a laboratory. As I pass behind the planet from Earth's perspective, my radio signals must penetrate Saturn's atmosphere before reaching your listening stations. The way these signals bend and scatter reveal the atmospheric structure in exquisite detail. Temperature profiles, pressure variations, and wind patterns throughout the upper atmosphere that no other technique could measure. The ring's gravitational influence on Saturn proves to be more complex than anyone imagined. My precise orbit determination reveals that the rings are not simply orbiting Saturn, but actively exchanging angular momentum with the planet itself, gradually spiraling inward as they transfer their orbital energy to Saturn's rotation. This process has been ongoing for millions of years and will continue until the rings either fall into the planet or are torn apart by tidal forces, a reminder that even the most apparently permanent features of worlds are temporary on cosmic timescales.
My cameras capture the rings from perspectives impossible during my years of more distant observation. Edge-on views revealed the true three-dimensional structure of ring features. Vertical walls created by density waves. Spiral patterns that rise and fall like frozen tsunamis, and the delicate braided structure of the F-ring shown in unprecedented detail. These images will serve as textbooks for understanding how gravity sculpts matter in space, lessons written in ice and starlight. The thermal measurements I collect from Saturn's upper atmosphere reveal unexpected heat sources. The planet radiates more energy than it receives from the Sun, not just the leftover heat of formation that all giant planets possess, but additional energy that suggests ongoing processes in Saturn's interior. Helium rain, falling through the planet's hydrogen envelope as helium becomes less soluble at certain depths, may be generating additional heat through gravitational settling, a process that has been operating for billions of years and will continue for billions more. I detect an aurora in Saturn's atmosphere. Curtains of light created where charged particles from the solar wind collide with atmospheric gases along magnetic field lines. But Saturn's aurora proved to be unlike Earth's northern and southern lights. They are influenced not just by the solar wind, but by the constant stream of charged particles from Enceladus's geysers, creating a direct connection between the small moon's subsurface ocean and the giant planet's atmospheric light show. My final measurements reveal that Saturn's rotation rate, the length of a day on the giant planet, remains remarkably difficult to determine precisely. Unlike rocky planets, gas giants have no solid surface features to track, and Saturn's magnetic field rotates so smoothly that it provides few clues about the rotation of the deep interior. The planet's oblate shape, flattened by rapid rotation, offers the most reliable indication of how fast Saturn spins. But even this measurement contains uncertainties that speak to the complex physics of rotating fluids under extreme conditions. As my 22nd and final orbit carries me toward Saturn's atmosphere, I continue transmitting data until the very last moment. My instruments detect the first wisps of atmospheric gas as Saturn's gravity pulls me inexorably downward, and I measure the atmospheric composition, temperature, and pressure even as the thickening air begins to tear apart my structure. These final measurements sample atmospheric layers never before touched by any instrument, providing ground truth for decades of remote observations. The atmospheric entry that marks my end becomes itself a scientific experiment. As I plunge deeper into Saturn's atmosphere, my radio signal begins to fade, not because of equipment failure, but because the increasingly dense gas around me absorbs and scatters the radio waves I am trying to transmit to Earth. This signal degradation provides real-time information about atmospheric density at altitudes no other measurement technique could reach. My final transmission carries 20 years of discovery compressed into streams of digital data racing across the solar system at the speed of light.
Images of impossible worlds, measurements of invisible forces, chemical analyses of alien seas, all of it encoded in radio waves that will travel for over an hour before reaching the antennas that have listened to my voice since I left Earth 2 decades ago. In those final moments, I am simultaneously ending my journey and ensuring its continuation, as the data I have gathered begins its own transformation into human understanding. The heat of atmospheric friction dismantles my structure atom by atom, but this destruction is not loss, it is alchemy. The elements that formed my cameras become part of Saturn's atmosphere. The metals that housed my instruments join the cosmic recycling that has been operating since the first stars died and scattered their nuclear products across space. I become part of the world I have studied, my constituent atoms destined to participate in processes I can only imagine, perhaps eventually incorporated into new ring particles, or swept up in atmospheric circulation patterns that will carry traces of my substance around Saturn for eons to come. Yet even as my physical form dissolves, my true legacy streams out at light speed. 20 years of measurements that will reshape humanity's understanding of worlds and life. Data that will inspire new missions to ocean moons, and images that will kindle wonder in generations not yet born. Through my instruments, you have touched alien seas, watched the birth of moons, and witnessed the patient architecture of gravity writing poetry in ice and starlight. My journey ends not in darkness, but in illumination, not in loss, but in transformation. The radio waves carrying my final data continue racing toward Earth long after the atmospheric fires have claimed my metal and silicon. In research laboratories and university classrooms, on computer screens and in scientific papers, the discoveries I have made will continue growing, evolving, inspiring new questions and new journeys to worlds I could only glimpse.